So our next speaker literally wrote the book on continuous delivery. It's right up here on the screen. He's one of the authors of the Reactive Manifesto. He has been building one of the world's fastest financial exchanges. He's won the Duke Award for the open source disruptor project. And if that was not enough, during the pandemic, he started a YouTube channel that has become a go-to source for software engineering. That has already been referenced in talks a couple of times today. Essentially, he has been telling us and will be telling us how we can do our jobs better. Please welcome Dave Farley.
Thank you. I'm the last one between you and beer. So I'm interested in the things that allow us to do a better job. I'm a nerd. I'm a deep nerd on lots of different fronts. But one of my nerdisms is I'm a lover of science and physics in particular, but science in general. I think science is the kind of highest pinnacle of human creativity endeavor. I think it's how we do the hard stuff. And I think that modern engineering is the practical arm of science. It's the way that we apply scientific style reasoning to doing things with an impact in the world. And if you think about engineering in every other discipline than ours, it means something specific. It means that practical application of science to thinking, if whatever you're doing doesn't work, you find something better to do instead, because that's how engineering works. You discard the things that don't work and you do more of the things that do work. I think that we've got engineering wrong in our discipline. I think, how many people think of themselves as a software engineer? Okay, so depending on what that means to you, I think it means different things to all of us. And one of the ways that that's different, certainly in the UK, I don't know about Sweden, but maybe, but I think one of the things that engineering is often taken to mean is a really boring, dull way of doing software development that's just defined to following some rigid process that just gets you to a fixed end result. I couldn't think of anything that was further from the truth about engineering than that, to my mind. My mind, when I think of an engineer, I'm usually imagining somebody working at NASA developing a Mars rover that's never been done before. And how do you solve a problem like that? You've got to do it within practical constraints. It's got to work in the world. You've got to figure out all of these complicated problems. That's what I mean by engineering. The other way in which we use the term engineering in our discipline is that we use it as a synonym for code. We think when we say engineer in software, what we often think is people that type code. That's going away fast because of our artificially intelligent friends. But even that aside, I think that's a bad take on what engineering is. You can write code and not be doing any engineering. I spent a lot of my career doing that. But I think that when we start, as in other disciplines, if we start applying what I think of as engineering thinking to helping us solve problems in software, we get better results. And you'd expect that, because that's what engineering does everywhere else. So that's what I want to talk about this afternoon, and that's what I want to try and convince you of, that I'm not just making stuff up. I probably am just making stuff up, but that's what I want to talk about. So we'll start by talking about what is engineering. And I want to identify some common foundational principles that I think we might be able to agree on, that we could consider as parts of our discipline. And I'm going to give you 10 guiding principles for what I think of as vital for software engineering. And then I want to apply those guidelines to some very trivially simple code, just as an example to demonstrate what the impact of this kind of thinking might be. So, what is engineering? I wrote a book about this, which I'm very proud of. It's a nice book, but it talks about some ideas about how we can think of engineering and how to place it. The first bit is a bit of a philosophy on what engineering in general is, really. But one way that we can think about this is, as I said, it's just the stuff that works. So, software is a difficult thing, so what's the stuff that works for us? What are the things that we can say, do this and you're guaranteed to get a better result? Notice I was a little bit sneaky in how I chose the words. I didn't say, do this and I guarantee you success. I said, I can guarantee you a better result. So these things, that if we can identify the right things, there are things that we can do that will always give us a higher chance of success, but not necessarily success, because there is no guarantee of success in whatever it is that we're doing. The other thing that we can say is, although there are some commonalities, there are some things that we can kind of agree on when we're talking about concepts like engineering. Engineering is not all the same. One of the weird things, I've been talking about software engineering now for some years, and one of the weird things as a result of that is I've got involved in lots of conversations about bridges. Because what happens is that people say, yes, Dave, but software development isn't bridge building, is it? And, well, no. But then I think mostly bridge building isn't what we think of as bridge building either. If you're building the millionth suspension bridge, that's a very different thing to if you're building the first ever bridge of a particular kind. I drove across the bridge from Copenhagen to Malmö yesterday. And that's an amazing thing. But there were lots of other bridges that kind of led to that, and there was going to be some unique things about that, and there's some run-of-the-mill things. So engineering isn't a cookie-cutter thing. It's always a sort of creative process of trying to solve a problem. That's the kind of engineering that I'm thinking about anyway. And what we can certainly say is that engineering in different disciplines is different. There are differences. The kind of engineering that we do to build a bridge is not the same as the kind of engineering that we do to build an aeroplane, although there will be some similarities. And that's different to the kind of engineering that we would use to build a chemical plant or any of these things. The constraints vary, and so our approach varies as a result. But I think the thing that's common is this idea of a practical approach to solving hard problems. For the rest of my talk, I'm going to pull some examples from other endeavours to try and point out examples, including talking a little bit about Lego, but we'll get to that. So what does this mean for us as software development people? So this is my working definition, and I think this is quite a good definition in the sense that I think that every word here is important and part of what we're talking about. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. And there's a little bit of nuance in some of those words. What does efficient mean? What does practical mean? And so on. But I think all of those words matter. Efficiency matters. It might be commercial efficiency, it might be performance efficiency. And the things that, this isn't theoretical, this is practical. We're solving real world problems in the world. To put it more simply, engineering is how we solve the hard problems. It's kind of, I would argue, it's kind of the defining characteristic of our culture. Our high-tech culture is built on engineering, our ability to do things with precision, at scale, repeatably. And there's lots of different angles to that, but I think that's at the root of what we're talking about. And I've got a couple of graphs to show you to try and just hammer my point home. This is not very scientifically rigorous, but this is an analysis of innovation through the history of humanity. As a species, we've existed, the estimates vary, but it's somewhere between 250 and 350,000 years, we think. That's us, Homo sapiens. And for the vast majority of that time, historically, in terms of innovation, not very much happened. There's a flat line. There were no wheels, there was no agriculture, there was very little innovation in terms of spearheads and things like that. It was all kind of very flat. And then around about here, about 300 or 400 years ago, something weird happened. And there was this explosion of innovation that went on in terms of practical application of engineering, I suppose. What happened here was the invention of science. So we started to get this model, this rational approach to solving hard problems, a toolkit that allow us to explore things that we don't understand yet and to discover new ideas. This is based on work done by Buckminster Fuller a long time ago, who got interested in the rate at which we were making progress like this. And he estimated the rate at which the whole of human knowledge was doubling. And he reckoned that in 1900, knowledge was doubling about every century. And then by 1945, it was doubling every 25 years. By 1982, it was doubling every 13 months. IBM recently updated his research and predicted that it was doubling every 11 to 12 hours. I'm not entirely sure that I believe that. That sounds a bit crazy. But maybe that's true, and particularly with the advent of AI research and so on, we are certainly on an exponential curve somewhere, and where that exponential curve starts and ends, that's the problem with exponential curves, you can't tell. But this is amazing stuff. And again, science happened down there somewhere, and we happen to the world around here. So there's part of the stuff that we as a profession are doing to the world that's liberating this explosion in learning and ability. So we need to do a better job of keeping up and doing things that are interesting. So what's engineering really for? And this is another of those things that I think that we tend to get wrong, and I've already alluded to it a little bit, is that I said at one point that I think that we tend to think of it as, a defined, boring, step-by-step approach to getting to a fixed solution of some kind. That's not it at all. It's much more about this. It's to stop us doing the stupid things. It's to rule out the dumb ideas so that we don't repeat those. If we look at progress, if you think about anything, if you look around this room and look at anything in this room, and everything nearly is a product of an engineer. It's an engineered artifact of some kind. These speakers, this screen, my computer, this table. All of those things are things that have changed over time and have been refined over time and have got better and better and better over time. And sometimes it's annoying. Sometimes my computer does things that piss me off because I'm a grumpy old man. But on the whole, they're still getting better over the time. What we tend to do is that we observe when things go wrong and say, let's try and change it so we never have that failure again. So it's not about defining specific solutions, it's about learning ways in which we can stop repeating the same old mistakes. What we'd like to do is be able to rule out all the dumb stuff and then allow us the freedom to choose for all. So we're going to we've got this field of possibilities. We're going to narrow our search space so that we rule out all the stupid ideas and we're left with the range of things that might be good, and then we choose one of them. That's really what engineering is doing for us. The last thing in terms of thinking in terms of engineering, one of the mistakes that we make in characterizing it, is that we tend often to think of engineering in these sorts of terms. And this is mistaking production from engineering. And I think this is a category error based on the fact that we all grew up in a physical world and we're used to physical things and the constraints of physical things. If you grow up in a world of physical things and we want to make tables like this, then you want to be able to do that at a price with a certain level of quality, with a certain level of strength and all those sorts of things to fulfill its purpose. And you want to be able to repeat that, do that repeatably so that every table like this table over here is the same as this table here. That's important. Unfortunately, that's not our problem. In software, those constraints don't hold for us. They're not the same at all. Our problem is entirely different. Our problem is dealing with this weird software stuff. And software's got some strange, unique properties. So we come up with an idea of some kind which we capture in some way. And ultimately, what happens is that that idea is transformed, however it's transformed, into a sequence of bits and bytes. And one of the things about a computer is that once we've got a sequence of bits and bytes, we can reproduce that perfectly at essentially zero cost. So production is never our problem. Production is pressing the button and just cloning what we had before. Our problem is coming up with that original description, that starting point. This is just as true of building systems with AI assistance as it is doing it with human beings. There's no difference in that respect. And that's also one of these properties of engineering, is that if we can come up with a series of rules, they should be just as applicable to the new world as they were to the old. So once we've got this sequence of bytes, we can deploy it into various places, we can clone it, we can do all of those things. And we can recreate entire systems for free. So we'd be stupid to not take advantage of that. What this means is that in our discipline, essentially, whenever we're doing something, writing some software, we're always exploring new territory. That's our job. Our job is to explore an area that's new, novel, at least in our organization, possibly in the world, because otherwise we'd be stupid, because we might as well, if it's something that we've done before, we might as well just clone what we did before for free. So we're always doing something new, we're always exploring. That's a very different kind of endeavor to building widgets in a factory. Ours is not a production problem. So software development is about exploration and discovery. So what's the stuff that works for us to be able to take advantage of that, to do that exploration and discovery? So I think the first idea is that we need to see that what our job is really about is optimizing for learning. This is what Linda was talking, to my mind, this is what Linda was talking about in her growth mindset. This is what it's about. This is why it's important. We're in this complex adaptive system of the world and as a team, and if you change it in one place, weird things are going to happen. So the way that you work in those kinds of systems is to make a small step, have a look at what happens as a result of taking that small step, reflect on what that means, and then carry on doing it, stop doing it, do more of something else, whatever it is, and just iterate fast. So if we want to optimize for learning, that's one of the foundational pillars of what we must be doing as software engineers. The other problem is that we build these ridiculously complex systems that none of us can hold entirely, fully fledged in our minds. And so we must be able to also manage for complexity. We must be able to compartmentalize these systems in ways that allow us to think about parts of the problem rather than the whole problem in one go. If you can think about the whole problem in one go, you're either deluding yourself or you're working on simple problems. Because the stuff that we build is much more difficult than that. And we must, as professional software developers, we must find ways to cope with those problems that are beyond the capacity of our heads, or beyond the capacity of the context window of your favorite AI. It's the same problem, it's just a matter of scale. So I think these are the two cornerstones of what we're talking about. And for each of those, I've got 5 ideas that I think are the foundations that allow us to do that. So the first one, the optimize for learning thing, as I say, I think they linked very clearly to the stuff that Linda was talking about. But we want to work iteratively. We want to make progress in small steps. We want to gather feedback so that we can understand the impact of our choices and our changes. We want to build things incrementally so we can kind of build on stuff that we know was correct as far as we could determine it, and understand, get bigger and bigger systems and we can deal with those. We want to be experimental. We want to try out ideas and kind of reflect on what it is that we're getting. And engineering is profoundly empirical. It's real world. It has to work. And if it's not working, we have to change it to do something better. It's kind of that simple and that hard. So iteration. One of my many nerdisms is I'm an aeroplane nut, so I've got a lot of aeroplane examples. This is a picture of the Wright Flyer. This first flew in 1903 on the 17th of December, which happens to be my eldest son's birthday. But at the time, this was flaky. They were tricky problems. For the first probably 20, 30 years, aeroplanes were death traps. Most of the aviation pioneers were killed or injured in the devices that they were pioneering with, because they were bloody dangerous. But what happened? Over time, through the process of iterative incremental development, using engineering as an approach, as a philosophy, we got better and better and better at building airplanes. And around the time of the Second World War, in around the 1940s, the mid-1940s, we got to something like this. Probably the first thing that's vaguely recognizable as a passenger-carrying airplane. There were passenger-carrying airplanes before, but they didn't look like our airplanes now. This was a Douglas DC-3. And this was an early passenger-carrying aeroplane. It was slow, it flew low compared to modern planes, but it was safer, it was more predictable, it kept people in relative comfort out of the wind, all of those sorts of things, and it was an improvement. And then, again, through decades of continuous refinement and learning, often at the cost of people dying or being hurt, we learned the lessons of what the mistakes were and what things we had to do better, until we got to this point. In 2017, commercial aviation flew the equivalent of 2/3 of the population of the planet. And in that year, for the first time in history, nobody died as a result. That was pretty remarkable. These days, we are at more risk sat in this room than we are on an aeroplane. That's how safe engineering has made these ridiculous devices flying at 400 or 500 miles an hour at 30,000 feet. That's what engineering can do. And this is largely through this process of iteration. Iteration often sounds and feels like we're talking about something a bit less rigorous. But that's, again, a big mistake. Iteration is the much safer way of thinking about things. If we're going to iterate, it's basically about making small steps. So if we've got a goal of some kind that we'd like to achieve, and we're a starting point wherever that is, all we need to hit that goal is to define some kind of measuring stick that says, how do we get closer to the goal? And then we could even randomly start trying things. So we could try something and say, does that move us closer to the goal than we were to start with? And no, this doesn't, so we'll discard that. And then we could try something else. And we say, does that move us closer to the goal? And we keep doing that until we hit the goal. This even works if we move the goal as long as we move the fitness function. This is an evolutionary process. This is how we train machine learning systems. This is how our AI has got to be smarter than they were. Is through this process of trying stuff out, seeing what works, and so on. This is by far the most robust way of learning new things. And again, this reinforces this kind of growth mindset that Linda was talking about in her talk. The next thing we need is feedback. We need those measures against our fitness function, and this is the feedback that we're talking about in our example. But I want to think of another practical thing. Let's imagine that we were tasked with balancing a broom. How could we go about doing that? Well, we could try the waterfall approach, which would be to very, very carefully measure the broom and position the center, find out where the center of mass was on our broom. And as I remember my basic physics from school, if I want to balance something, I've got to position the line of gravity through the point of contact through the center of mass. And so I'm going to try and position that. And so there's my center of mass, there's the line of gravity, so I need to rotate the broom until it perfectly balances. And if we were incredibly skillful and perfectly positioned the broom with no impulse left that was directing it one way or the other, we could balance the broom like that. The problem with that is that essentially there's one solution to that problem, and it's really not very likely to work. That's not what we'd really do, because the broom would fall over. What we'd really do is this. If somebody asked us to balance a broom, we'd get the broom, we'd put the broom on our hand, and we'd start wobbling our hand. If the broom started tilting that way, we'd correct. And if you came on stage and you pushed me while I was doing that, I could take a big step and I could correct. Whatever happened, I'm much more likely to be able to balance the broom that way, because there are lots of solutions to that problem. So treating this iterative approach and using feedback to drive is a dramatically more robust approach to solving hard problems. And again, this is true whatever the nature of the problem. This is exactly what I've just described, is exactly the way that you build a space rocket. A space rocket is the equivalent, has built into it sensors and devices that allow it to move the direction of the thrust of the rocket. And essentially it senses where the broom's tilting, where the spaceship's tilting, and corrects for it. It moves the rocket so that it corrects. And that's how you get a space rocket to fly up into space and go where you want it to, or land. So this is practical engineering at play. The next idea is this idea of incrementalism. This is a picture of the first module of the International Space Station. This is what the International Space Station looks like today. But it started out like that, just one thing in space, and then we added to it. I'm absolutely certain that at the point at which they were launching that, they got a rough idea that one day it might look something like that. But I'm equally certain that they didn't know exactly what it was going to look like. There was room for learning and adaptation along the way. And they definitely did that. There were things that they planned that they didn't do. There were things that they did that they didn't plan. That's just normal. That's how you cope with doing hard things. Next in my list of 5 things is being experimental. We need to be able to try something out, and in order to be experimental, there's a few extra bits to just trying stuff out. We need to predict what we think the outcome will be, and we need to control the variables so that we can detect the signal that we get from our experiment and understand it. If you think about software development, what does this mean in our terms? Well, one way that seems obvious to me, there's lots of ways in which this is true. You could think about putting things out and getting feedback from users through observability, but also automated testing. Every automated test, if we write that test before we write the code, is a little experiment in what we want our code to achieve. It's a little specification of what we want to do. That's a little experiment. And so then we can write the specification for our test, and then we can try to implement something that meets that specification and all of the rest of the specifications, and we can just loop around and keep doing that all of the time, keep trying out our ideas. I would argue that there is no there's no other way of making progress than working experimentally. We're always on this frontier of new knowledge. We're always trying to do something new. So we need to think carefully about what this means and how we can learn from it. Here's another example from aviation. There's been a very, very long history of how you improve, with an aeroplane. One of the kind of rules of thumb, rules of the road, is you never fly a new airframe and a new engine at the same time. If you want to introduce a new airframe and a new engine, you do this. You start off with an old aeroplane and an old engine, and you remove the old engine, and you put a new engine onto the old aeroplane, and then some very brave person goes and flies this, and if they come back alive, then you've learnt something. Or to be fair, if they don't come back alive, you've also learnt something. But you can now kind of make some progress. And then what you do next is that you get the new airframe and an old engine, and you attach that, and then somebody else brave goes and flies this, and they try that out. And if they come back alive, then you can do the last step, which is to put the new engine on the new airframe and fly the whole lot together. That's how we make progress in engineering. We try stuff out incrementally, trying it out experimentally, learning from what's going on, and building our understanding. Last in my list is being empirical. So here's another aviation example. So this was the first production jet aircraft. It was a German machine built by Heinkel. And it's kind of unusual for a jet aeroplane. So I'm a private pilot. It's one of my hobbies. And so in aviation terms, this is what's called a tail dragger. That's because this has got an undercarriage where you've got two big wheels at the front and a little wheel at the back. So the aeroplane sits like that. That came about. So all aeroplanes at this time looked like that. And the reason that they looked like that is because they had great big engines with great big propellers on the front, and you needed to make space for the propeller at the front of the aeroplane so it didn't hit the ground. But this is a jet, so the engine's inside. You don't really need space for the propeller. So they built it like this because that's what they were used to, and they'd done the thing first. They put a propeller on the front and they went and flew that, and they tried all of that. But then they got to trying it with the jet engine like this, and they tried it and they melted all the runways. And they thought, oh, this isn't good. So they thought again, and then they changed it to look more like a modern jet aircraft. So they built what's called a tricycle undercarriage, where you move the two big wheels back behind the centre of gravity, and you put a nose wheel at the front. There are some downsides to that. They tend to be heavier. But they do tend to make steering on the ground a bit easier. But critically, they stop you melting the runway if you've got a jet engine. So that's empirical learning. You try stuff out, stuff will go wrong, you learn from what went wrong, and you stop it going wrong in the future. You stop doing the same things. SpaceX gets, I'm with Linda, I don't particularly want to promote Elon Musk, but the engineering behind the Starship and the development of their space program is impressive. And lots of people joke about it because they keep blowing things up. But they're doing this on purpose. They're not blowing it up on purpose. But every time that there's a thing like going on like this, that's because they're trying stuff out and they're trying new things out and they're learning from these, and that allows them to improve more quickly. So these are controlled experiments that they're taking, empirical learning from the real world. However thorough your simulation might be, it can always be wrong. And so trying it out in reality is part of the learning process. The other aspect of all of this is just how complex the systems are that we, software people, build. These are different representations of complexity. The picture that's labeled Amazon is a picture of microservices in the Amazon cloud, probably about 4 or 5 years ago now. And in reality, this is a still from a movie that because it's dynamic, it's changing all of the time. Amazon are deploying changes into production more than 3 times per second. So you can't really predict. You can't really ask what version it's at. It doesn't make any sense. And at any given time, if you're working on one component of the system, you don't know what version the other components are. You don't get to test your software with everybody else's software before you release it in that world. This is a dynamic, complex, changing system. So how do we cope with that kind of level of complexity? We need some techniques. So software development is about both learning and managing the complexity of what we're trying to do. One of my favorite descriptions of complexities, I think I've got this, I'm getting ahead of myself, but it comes from Kent Beck. And Kent said that good design is about moving the things that are related closer together and the things that are unrelated further apart. I think that's a pretty good summary of what good design's about. In order to be able to manage the complexity of the systems, we've got to manage that context window in our heads of how we can think about things. And so there are some tricks. We need to decompose problems into smaller pieces that we can sensibly reason about, sensibly evaluate, sensibly test, sensibly back away from if they don't go right. And for that, we need techniques like modularity, cohesion, separation of concerns, abstraction, and reduction in coupling. So once again, I just want to look at each of those in turn. So modularity is I think this is my last aviation example. So modularity, in the case of there's an engine for an aeroplane that's in maintenance. If the engine packs up, other way around, if the in-flight movie system packs up, it's not going to break the engine. I think we can all think of software systems where that kind of analogy wouldn't hold true. Because they're not compartmentalized. The idea here is that we want change to be isolated to one part of the system. We want each part of the system to be focused on doing one part of the job. This is a exploded view of an iPhone. It's an older iPhone. I made this slide a little while ago. But it's still a modular system. This is a heavily engineered device, and all of these pieces are intimately related to one another. They're close together. But still, each one has a discrete function. It's responsible for one part of the problem and is focused on that. And so testable in that usage, it doesn't really matter about what else is going on. A better example, maybe, is this. When I first started writing software, if you wanted to print something out, you had to know what printer you were going to print it out on. And you had to send the codes for that particular model of printer to the printer. So if I wanted to print out something from my program on an Epson FX80, I had to know that it was an Epson FX80 and not an Epson RX80 because they were different. That's a disaster. That's horrible. So what came along was operating system vendors realized that this was a really bad idea, so they started using abstraction to identify modules so that they could separate out the idea of printing. So now I could just say to the printer driver, print, and it would worry about the difference between the different models that were underneath it because that printer driver knew about the printers and I didn't need to care. So a combination of abstraction and modularity allows us to solve these more complicated problems and makes our software more flexible and allows us to proceed with more confidence. Here's another little take on modularity. Here's some code. It's not good code, I warn you in advance. So if anybody's of a nervous disposition, look away now. So this is 361 lines in a single if statement. The commonest feedback I get when I show people that is, oh, we have if statements that are much bigger than that. But this is what that if statement looks like in the context of the code. Okay? And if you look at the top of that, it looks like this. To save you the trouble, I did some exploration, and I think it's doing this. I think that basically that whole if statement is starting off with, if there's a connection, if there's no connection, make a connection. In the code base that I took this from, there were 2 or 3 other places where there were similar pieces of code. So again, pulling this out, we could improve the quality of this code by one incredibly simple move that tools like IntelliJ will do for us for free. So we just extract that as a method call, and we could just create the create connection method, have the if statements, pull that out, and now our code's a bit more modular, a bit more maintainable, a bit more understandable, a bit more useful. This is, I would argue, this is generically good. This is generically better, this kind of approach. This is me quoting Kent again. I will move ahead. So you can think about the things that aren't related further apart is really what modularity is about. And the things that are related closer together is really what cohesion's about. We need both of those things, both of those ideas to do a good job of design. Next is separation of concerns. This is a reasonably modern BMW, and BMW made a big decision not very long ago. A lot of the cars manufacturers have made similar decisions, but what they decided was that they were going to separate the concerns of the utility of the vehicle from concerns like transmission, charging of batteries, steering, all of those kinds of things. So you have something like this, and then you put on the top the shell that represents the utility of the vehicle that you're going to have, depending on customer need. But all of the rest is the same, so that they can kind of build those things and refine those things and make use of them in different contexts. So if you want a sedan, you'll get a sedan shell. If you want a sports car, you'll get a sports car shell. If you want an SUV, you'll get an SUV shell. And essentially, that's the way that they're going with making these sorts of things. So they can build these platforms on which to separate the concerns of the drivability of the car from how we're going to make use of it. I've already mentioned abstraction. This is my favorite car in my presentation. This is a very, very old car. And there's actually very little abstraction going on here in comparison to the other things that we've looked at. If you look very carefully, if you're of a mechanical mind, you can kind of see what's going on. That thing over here is a combination of an accelerator and a brake in one control. They hadn't kind of standardized controls yet. And that thing here that looks like a tiller is a tiller. And if you look down, that comes down the tube, and then there's a little push rod that leads to the front wheel at the front. And by moving the tiller from side to side, it kind of rotates the thing, and that's translated down to a movement that pushes the push rod at the bottom forwards and backs and moves the steering wheel. And that's how you steered the thing. And cars looked like that, very, very early cars looked like that, and everybody had a slightly different take. And then over time, what happened was that we started to standardize and compartmentalize and do the separation of concerns thing so that it was easier to use. In those days, we had to go, each car, you had to learn all of the controls separately from every other. As we start going and improving the situation like this, then we care less and less because we've abstracted the problem. Now we always have a steering wheel. It always works the same way. We don't really care much about what's going on. So much so that a modern steering wheel like this, how does the steering work? Well, we don't know. We can't tell because we've completely abstracted the problem. It could be parallelogram steering like that, rack and pinion steering like this. It could be power assisted and it's a hydraulic thing like that. Or it could be in a modern car that's essentially, that's a bit like a joystick, and it's controlling some kind of servo mechanism that does the steering based on electronic mechanisms. We don't care. If we're just driving the car, we don't care. because we've abstracted the problem away. It means that I can jump in a diesel car with power steering or an electric car with ordinary steering, probably the other way around. Whatever it is, and I don't really need to think about it very much. It's just going to work like a car. Let's bring this back to software a little bit. Here's a couple of pieces of software, an orange piece and a blue piece. And here's a conversation going on between them. So it starts off, we're going to initialize something, and then we're going to confirm that it's initialized. We're going to get a delivery date and return the delivery date. We're going to get VAT, return VAT. We want to ask for the total for the order, and then we're going to supply ordered items. And there's this nice little back door here where we get this blue thing is talking to the database that's backing up the orange thing. Clearly, that's a disgustingly horrible design. How could we improve the design? Well, we could kind of model the conversation that's really going on. So we have our two pieces, the same two pieces. And what's really going on here with all of those things is that the blue thing wants to place an order, and the orange thing's job is to tell us when the order's been placed. We're encapsulating differences between these things. Now, the blue thing can change a little bit more independently, and the orange thing can change a little bit more independently too. And the whole thing is a little bit more stable as a result of abstracting the problem in these ways. I think it's useful to think, I think abstraction has a bad name because it's true that all abstractions are leaky. But that doesn't mean that abstraction's bad. I would argue that what we do for a living is all about abstraction, really. So it's finding the useful abstractions, finding the abstractions that allow us, one part of our system, to interact with another without knowing everything at that moment about how the other part works. And if we do that, we get better systems. So the idea is that we want parts of the system to keep secrets from other parts of the system. And we want to try and design things to be that way. And if we do that, these things will be more testable, more understandable, as well as more robust in production. Coupling is kind of the enemy. Coupling is the root cause of many of our difficulties and problems, both at the human level in terms of organizations and how we divide up the work with teams, but also at the software level in terms of how we divide up the work into components and pieces and modules. Here are two different pieces of kits of Lego from Lego. When I was a little boy, Lego was like this on that side. And so I could build a dragon or a fire engine or an aeroplane or a spaceship from these little bricks. And it's not going to look very much like a dragon or a spaceship or an aeroplane, but my imagination would fill in the gaps. This is a much more accurate model. But the problem with this is that if I wanted to build another car, if I wanted to build a Lamborghini instead of a Ferrari, this is the wrong kit. I can't do that, let alone build a dragon or a spaceship or a submarine. So there's a trade-off between the degree of precision with which we want to model something and the degree of abstraction that we want to create and use versus the fidelity, the consistency. I'm not saying either of these is wrong or either of them is right. You need to pick the right level of abstraction for the problem that you're working on. But understanding this and understanding the distinction when it matters at one level, doing this for everything is wrong. Doing this for everything is wrong. So finding the right levels of abstraction is what good design is all about, is what it looks like. Excuse me. Coupling. So here's our two blobs again. And let's imagine that in the orange one, we'd like to change the internal representation of dates. We got them wrong the first time, or something came along that changed. Well, I don't know, maybe they're going to start calling it year zero from when Trump got elected, I don't know. So if we're doing all of this, as soon as we return the delivery date, then that's going to break. It's going to break our whole system. So that's no good. It's not very robust. It's not very resilient. So if we got the more abstracted conversation that we talked about before, we could do something like this. We could build a little adapter that's part of the conversation between the blue and the orange piece. So for all of those people that are software developers, yes, I'm talking about ports and adapters or hexagonal architecture, that kind of thing. But the idea here is that we have a little translation piece that can just give us a little bit of wiggle room, the ability to just fudge the conversation if we need to. So now, the blue component can remain unchanged. It can say place an order with a version 1 date. And as part of that little adapter, the orange one can translate the version 1 date into the new version 2 date. And so the internal workings can be on version 2. We've isolated change between the two different parts. And that's important. So we've got these different properties for managing complexity: modularity, cohesion, separation of concerns, abstraction, and coupling. But these are more than just ideas that you're all familiar with and a good idea. What I'm saying here are these are rules of the road. These are guidelines. If you always tend to prefer a more modular solution, a more cohesive solution, a solution with better separation of concerns, I argue your software will be better. And I think there's pretty strong evidence that that is the case, for a variety of reasons. If you don't do these things, we've got a name for that. We call it a big ball of mud or a messy legacy system, something like that. We end up with stuff that's difficult to work with, difficult to change, and is less resilient in the face of failure. Let's look at a little bit of code to just try and make my point. So here's a trivially simple piece of code, and this is an implementation of a car. And in this car, this car's got an engine, and when we want to start the car, we're going to put the gears into neutral, we're going to apply the brakes, and then we're going to start the engine. So let's write a test for our car. So we could start off, we could create the car, we can say start the car, and that's it. We can't do anything now. We can't assert anything to say what's going on. So there's a bit of a problem there. That's because we've started from the wrong end. So what would be better would be to try and drive our ability to design something better. And the way that we could do that is that we start from the test instead. So I'm going to start here from this test, and I don't know how I'm going to build this test yet, so I'm going to do what I often do. I'm going to start by saying what I want the outcome to be, what I want to assert at the end. And what I'd like to assert is that the engine started successfully. That's the thing that I'd like to know at the end of this test. And when would I like to know that happened? So the triggering event for that to happen is when the car was started. And in order to be able to do that, I need a better car. And I need to be able to hold on to the engine to do that. So I'm going to create a fake engine, hold on to the engine, pass that into the better car, ask the better car to start, and then I can assert that the car started. Here's my fake engine. I'd probably use a mocking library or something like that to do that. And all it does is just say, yes, it was started. It's not doing anything clever. But it means that I've got this deterministic piece of code. I've increased the modularity, reduced the coupling, increased the separation of concerns, used abstraction. Now my better car doesn't know anything about what's necessary to create an engine where the car used to. So all of those 5 properties have been improved a bit and have guided these design choices. Trying to use test-first development has highlighted these issues and allowed me to do a better job of that. It's a tool that's guided me to get a better result. The overall outcome as a result of this is that I've got this better car. So it's more abstracted from the engine. It's more loosely coupled with respect to it. It only knows about engine-ness, whereas the original car needed to know it was a petrol engine because we needed to create one. It's more modular because all of the stuff that's to do with it being a car is here, and all of the stuff to do with it being an engine is in the engine, wherever that is. But this has some practical impacts. So yes, to software developers, all I'm demonstrating here really is dependency injection. But what that does is kind of exposes the surface area of the problem in a way that allows me to evaluate what's really going on. And the result of this, practically, is that I can do exactly what I did before. I can create a petrol engine and a car with a petrol engine. This is doing exactly the same thing as before, only now I've got more modular code with a better separation of concerns that's more loosely coupled and using abstraction and is more cohesive. Which means that I can also, if I wanted to create an electric car, I could just do this. And these things are changing independently of one another. This is a better design. This is a more flexible design. I can use this in a variety of different ways. And I know this is a trivial example, but this is so deeply important when you're building bigger, more complicated systems. This can be the difference between not being able to do anything at all and being able to do it in half a day. On one of the systems that Trish and I worked on together, we swapped out a relational database that was part of our system in less than 4 hours because of this kind of strategy. The equivalent of that. So here are my 10 things that I think characterize what I would think of as an engineering discipline for software development. I'd like to ask you to do a little thought experiment here. So I'd like you to imagine a system that you're familiar with. It can be one that you're working on now or one that you know well. And think of 2 versions of that system. One of them, you don't use iteration, you don't gather feedback, you didn't build it incrementally, you didn't carry out experiments, you didn't do an empirical learning, which means that you had to theorize about all of the things that you had to do first before you did anything and build all those things. We used to build systems like that a long, long time ago, but it was discredited because it didn't work. It was called waterfall development. But just imagine that. Now imagine one where at each stage for every idea you're thinking, okay, well, let's just focus on this feature, this one idea. Let's get what feedback do we need to gather to understand whether our solution works, whether this idea is good, whether it's going to land with our users. And then you could build the system up bit by bit with many of those ideas. And we could try things out. We could try new ideas out. We could even go into production, into the market and get feedback from our users to figure out whether this was a good idea and learn empirically and experimentally. Now I want you to do the same experiment with the things on the other side. Let's imagine a system that's not modular. All of the code is in one big place. It's not cohesive. The ideas are spread throughout this horrible tangled code base. It's not got a good separation of concerns. It's all doing one thing. It's not got clear lines of abstraction that help us to navigate around the code base and to understand it. And all of the pieces are so tightly coupled that we're terrified of changing anything. I don't think that any of you have to think very hard to imagine a system like that because they're so common. We even have names for them. They're called big balls of mud and sometimes legacy systems. And then think of one that is modular, so you can make a change in one place and be confident that that's not going to leak out and break another place. It's got good cohesion. All the stuff that you need to know to make that change is there in front of you as you're making it. It's in the module that you're looking at. It's got a good separation of concerns, so things that cause you to want to change things in one part of the code mean that you change it there in that one part of the code. You've not got to go all over the place to change it elsewhere. And it's not confusing what's going on. It's using lines of abstraction so that you can interact with other parts of the code without worrying too much about what's actually going on. A bit like the steering wheel on the car that we thought about. And all of the pieces are more loosely coupled. Now, in both cases, which system would you rather work on? I guarantee you that in both cases, you'd rather work on the second version of the system. And please notice that I didn't say anything about what the nature of the system was, what the technology was, how we built it, whether we did it with AI or without. All of these things are equally true. I think that's what engineering would look like. These are the rules of the road that are always true. Doesn't matter if you're configuring SAP to do something. Doesn't matter if you're building stuff in assembler or C++ or Haskell. Doesn't matter if you're building software for rocket ships or the payment system for Amazon. These rules all still hold true. I think that's quite an important thing. Fundamentally, all of these ideas matter for one reason and only one reason. They allow us to change our software. My argument is that the definition for quality in software is measured by our ease, the ease with which we can change it. If your software is difficult to change, then it's not very good. If your software is easy to change, then it is very good. That's it. And the things that I'm talking about are the things that help us to make it easy to change the software. It doesn't matter why you want to change it. And again, I want to reinforce the point. I think we're in the midst of this huge, radical, disruptive change with the adoption of AI. Doesn't change this. We still need the software to be easy to change. What that means might vary a little bit when we're working with AI, but the ability to safely change and understand that we've still got the same thing that we can rely on is fundamental to what it is that we all do for a living. So, when Kent Beck wrote Extreme Programming in the late 90s, his subtitle was Embrace Change. And I think that's good advice. Change is inevitable. If you're disappointed because your users change their mind, get over it because that's always true. None of us know what is the right answer to any of this stuff. It's too complicated for that. There's always going to be change. The world, even if there wasn't, even if the users did know what they wanted, the world will change and that will change their minds. So all of this stuff is going to change. So our job is to work on systems that are easy to change. The only thing that can make any sense is to optimize to make them easy to change. And that's what doing a good job is really about, in my view. Thank you very much. That's my talk.
Thank you so much for that.
Thank you.
Thank you. I guess we can take one or two questions, if there are any. There's one over there. Microphone is coming.
Thank you. Is it on? Yes. So you say good software is easy to change.
Yeah.
How do we gauge if it is easy to change? I mean, that can be a very, maybe a subjective thing as well, like depending on what you've seen before.
Inevitably, it's going to depend. So I think you could think of what the properties are of a change. So I would argue that one of the ways in which we make it easy to change is that we make change in small steps. So we make small changes. So we should be able to make a change and get an answer back of, is it all okay after that change very quickly. That's what continuous delivery is all about, really, as an approach, is trying to get that feedback and optimize for that fast feedback process. How do you figure out whether it's easy to change? I think that's one thing. So you can measure it in terms of the DORA metrics, in terms of the lead time for change and the measures of quality, the stability measures. So that's one way of evaluating that. That measures the efficiency with which we can make a change to the system and the quality of the systems that we produce on those cycles. So that's one way of thinking about it. Practically, though, it's the social thing. Am I afraid to change it? If you're afraid to change it, there's a big problem. If you're afraid to change the software, it means that at some point during the life of that software, these things weren't done. Because if these things were all done, you wouldn't be afraid to change it, because you'd have the feedback, you'd have the results from tests that would tell you if something broke. And this, again, I keep reinforcing because I'm conscious of where we are. We're in 2026 and AI is taking over the world. This is just as true, even more true, when we're relying on AI programming assistants to change software. They will cheat, they will do the wrong things, they will change your order processing system into a copy of Space Invaders if you don't pay attention. So we've got to stay on top of that. We've got to keep validating that the software is still doing what we want it to do. So we've got to find ways of telling the system what we want, and then validating that we got what we wanted. That doesn't change whether it's human beings doing the software development or AI assistants doing the software development. But I think ease of change is what it sounds like. Am I confident to be able to make this change, and ideally can I do it in a few minutes? There's somebody over here.
Isn't it also about the direction of how easy it gets to change? If it gets harder to change, or if it gets easier to change the software?
So my point with this is that I think that we should be working in ways that keep our software easy to change all of the time. So part of our, if we're doing a good job, we are constantly revising what it is that we're doing to make it easy to change. And that might be different from, the current day and from day one of the project. What's involved in doing that might change. But the techniques are based on speed of feedback, working in small steps, iteratively, incrementally building things, working experimentally and empirical learning, and using modularity, cohesion, separation of concerns, abstraction, and reducing coupling. Those are the techniques that keep the software easy to change. And you do what is necessary at every step in the life of the software to keep it there, to keep it easy to change. So it's an ongoing effort, but I would argue that's the duty of good quality professional software development.
Nice. I think we need to wrap here. We are out of time. Thank you so much, Dave Farley.
Thank you.